All right, so that would conclude this chapter, and we are going to begin electromagnetic field, electromagnetic waves. So first, let's talk about some basics about the concept of waves. Well, waves is just a disturbance in non-absorbing, non-dispersive media, and it can be described by some function. All disturbances can be described by some form of function. But if it's a wave, it must satisfy some specific conditions, those functions that describe the disturbance. So that is one form of disturbance, but for it to be a wave, this condition must be satisfied. So suppose f is the function that describes the disturbance that I showed you earlier, as a function as a wave travels along the z direction at different times, it's described by f. And if it's a wave, this function must be equals to g of z minus vt at the time, at earlier time, or you can also make it plus to talk about at a later time. So functions that satisfy these conditions represents a wave. So some examples which satisfy this condition that can be considered as a wave, and some that does not is given there. So you can look at it pretty straightforward. So I'm going to go through that. So before we talk about electromagnetic waves, it's important to know the general form of the wave equation, and we will consider a simple wave that most of you probably have seen in Intro Physics 1. In Intro Physics 1, I think the last activity is about measuring the frequency of a wave that's created on a string. I don't know, how many of you have taken Intro Physics 1? Yeah. So you remember a string tied at one end and vibrating. So you see the waves is propagating. And if you remember there, you used this relation to find the speed of the wave, which is determined by the linear mass density of the string so you remember this, where T is the tension on the string and mu is the linear mass density. So that's how you determine the speed on a string. So let's see if we, and this is the basic wave equation. You might have seen this one in TO. Well, we have already seen in TO this one. And let's see how this wave equation can be determined from a simple Newton's second law. So basically what I'm showing you here. So this is what you probably so that's a wave on a string. So if I stop it at some point, and let's consider just this part. If you consider only this part, so it was on its equilibrium position was along the straight line. Now, if I consider 2 points, one somewhere here, and let's call this is the z-axis, and here is the displacement as a function of z-axis, and let's consider 2 points on the string at some instant of time at z0 and at z0 plus delta t, that's more displacement delta t. So if I look at the string at that instant, what you would have is Yeah, so this is the situation that you have. So this is waves. So what we will consider is wave on a string. So if you consider the displacement of the string as a function of the at different times, so this is f of z, and also depends on time t, and just the instant that I showed you here. So somewhere here and here, 2 points. So I will call this one, just to avoid confusion, I will call this is z naught instead of d, and this one is z naught plus delta z. And the string is under tension, and the tension force on the string is the same. So let's say this is T, and this one is also T. But the angular displacement is different. So I will call this one is theta, and this one is theta prime. So we are interested in the vertical displacement of the wave. So what is going to be the net force acting on the string in the along the vertical displacement direction? So if I want to find F net, that's going to be T sine of theta prime, T sine of theta prime minus T sine of theta, yes. So this means F net is going to be T times sine of theta prime, sine of theta, theta prime minus sine of theta. Usually these angular displacements are small. All right. So for a small angle, I can express sine as tangent, right? You agree? T is going to be tan of theta prime minus tan of theta for small angular displacement. All right? But how can we express tangent of theta prime at this point if I use calculus? You know, tangent is vertical increase over horizontal increase, right? But in terms of derivative, how can I express tangent in terms of this function? Yes. So I can express tan of theta prime as the derivative of f with respect to z evaluated at what? Yes, z naught plus delta d. Similarly, tan of theta df by dz evaluated at z naught. So